Welcome to Submodule 2 of Directional Well Path Design. In this session, we build upon the basics covered earlier to explore the more complex aspects of trajectory planning. We'll explore tortuosity, kickoff depth, reservoir entry design, and operational considerations, blending technical principles with practical drilling lessons from field experience. The objectives of this module extend the foundation from Submodule 1. You should finish with the ability to critically evaluate how kickoff depth, trajectory geometry, and reservoir entry affect overall well performance. As a drilling engineer, trajectory planning goes far beyond simple geometry. Every choice impacts torque, drag, hole cleaning, and long-term wellbore stability. We'll discuss how to balance mechanical and hydraulic limitations against reservoir requirements. This involves careful casing design, realistic dogleg severity targets, and alignment with the completion strategy. Engineers must also integrate geomechanical knowledge. Formations with walk tendencies or anisotropy must be anticipated to prevent unplanned sidetracks or costly corrections. Another key outcome is understanding trade-offs. A shallow kickoff point may simplify trajectory and improve hole cleaning, but can extend measured depth. A deeper kickoff point may save surface distance, but introduce high doglegs and mechanical stress. Likewise, J-type versus S-type trajectories represent compromises between displacement, zonal isolation, and cementing effectiveness. By the end, you should be able to rationalize well path selection not only mathematically but also operationally, making plans that balance drilling efficiency with reservoir and completion requirements. When designing a well path, there is no universal solution. Each case must balance multiple engineering and geological factors. Critical considerations include mechanical stresses on the drill string, hydraulic efficiency, minimizing drilling time, and maximizing performance. Reservoir characteristics, fluid type, and completion design also play central roles. For instance, extended reach wells often demand shallow kickoff points and higher tangent inclinations, whereas faulted or unstable formations may dictate conservative build rates. The well path must also accommodate casing and cementing programs, hole stability, and cuttings transport. Optimization usually requires trade-offs, where design iterations balance cost against risk. The key is not to force the well against natural geological tendencies, but to integrate them into the trajectory. Ultimately, the best well path is the one that meets objectives safely, economically, and with long-term production efficiency. A basic rule of thumb is to kick off as deep as possible. The first kickoff should have a low build-up rate to limit the side forces. This enables the use of simple, low-cost assemblies, which reduces well construction costs. Keep the tangents at an inclination of less than 40 degrees or greater than 60 degrees to avoid hole cleaning issues. Place the end of the build towards the end of the drilled section. This enables better cleanup of the section and reduces casing running issues. As inclination rises, so will issues with wellbore stability and tortuosity. Tortuosity refers to excess curvature accumulated along the wellbore, measured at survey intervals and expressed as dogleg severity. Microtortuosity, in contrast, is the invisible crookedness between survey stations that cannot be captured by conventional measurements. Though small, it can significantly affect torque, drag, and casing wear, becoming a hidden operational hazard. Studies show tortuosity results from bit mechanics, formation variability, and motor steering effects. Rotary steerable systems, when properly deployed, can mitigate both tortuosity and microtortuosity, producing smoother wellbores compared with conventional steerable motors. High tortuosity increases the risk of stuck pipe, poor hole cleaning, and reduced life of downhole equipment. Therefore, managing tortuosity is essential not only for drilling efficiency, but also for future completion and production operations. The kickoff point, KOP, is the measured depth where the well begins to deviate from vertical. Its selection has a profound impact on the well profile. Shallow kickoff points generally reduce dogleg severity in the build section, allow for better hole cleaning, and support long lateral displacements, making them common in extended reach drilling ERD. However, They require more directional control. Deep kick-off points lead to higher inclination angles and potentially severe hole cleaning challenges. They also increase the risk of torque and drag. Optimal KOP selection balances target geometry, formation stability, and operational risk. For example, formations prone to instability should not be chosen as kick-off point zones. The kick-off point decision integrates geoscience knowledge, drilling mechanics, and long-term well objectives. Although mathematical models can generate numerous well path options, not all are practical. Lithological data often reduce the range of suitable kick-off point depths, as unstable formations, faults, or salt zones must be avoided. For instance, a theoretical design might allow for a deep kick-off point, but operational risks like high torque, drag, or unstable build sections may render it impractical. Engineers aim to select trajectories that are rational, simple, and aligned with natural geological tendencies rather than opposing them. Ultimately, practicality is determined not just by geometry, but by the integration of mechanical, hydraulic, and reservoir considerations alongside cost and safety constraints. This ensures the design is executable in the field and optimized for completion and production phases. This slide illustrates how kick-off depth changes well geometry for a target at 10,000 feet TVD and 7,875 feet displacement with a fixed build rate. The shallower the kick-off point, the lower the tangent angle, and the shorter the measured depth to TD. This relationship has profound operational consequences. Shallow kick-off points reduce inclination, easing hole cleaning and simplifying casing operations. They also minimize torque and drag by distributing curvature over a longer section. However, they often increase MD, adding drilling time and cost. Deeper kick-off points shorten MD, but concentrate doglegs, increasing mechanical loads and the risk of reaching torque or drag limits. As an engineer, one must consider not only the geometry, but also operational capability. Rig horsepower, mud pumps, and drill string design may all be limiting factors. Additionally, shallow kick-off points allow more flexibility in managing azimuthal corrections early, reducing course corrections later in the well. Ultimately, kick-off depth should be selected not just on paper, but through integration of rig capability, BHA design, hole cleaning hydraulics, and reservoir entry requirements. The optimal solution balances measured depth, inclination, and operational risk to deliver a trajectory that is both drillable and productive. Shallow kick-off points are often favoured for offshore and ERD wells. They enable the build-up section to be cased early, reducing risk in potentially unstable formations. This design allows for long horizontal displacements and tangent angles greater than 50 degrees, which is ideal for maximising reservoir contact at shallow depths. However, shallow kick-off points require careful management of build-up rates. If build-up rates are too high, torque and drag values can increase dramatically later in the well. Therefore, shallow kick-off point designs typically employ lower build rates, ensuring smoother drilling mechanics. When implemented correctly, shallow kick-off points provide flexibility, enable casing programs to isolate unstable formations early, and extend well reach, all while minimizing risk to drilling and completion operations. Reservoir entry design significantly influences drilling and production performance. A general rule is that the drop rate should be around 50% of the build rate to minimize buckling in the curve. J-type and S-type profiles show clear differences. J-type wells with simpler geometry tend to generate less torque and drag, making them mechanically favorable. In contrast, S-type wells, often drilled for production reasons, maintain tight tolerances on reservoir entry angle, sometimes within 5 to 10 degrees. This is especially important in gas reservoirs, where casing cement quality is critical to prevent gas migration during setting. Reservoir entry planning must consider lithology, pressure regime, and completion strategy. The entry angle not only affects wellbore stability, but also determines long-term productivity and ease of artificial lift application. This slide highlights the trade-offs between J-type and S-type profiles when entering the reservoir. Both may reach the same target, but their geometry and implications differ significantly. J-type wells are simpler. With a single build and tangent, they provide more stable torque and drag behavior. They also tend to produce lower tangential angles, making casing runs easier and reducing completion risk. For most oil wells, a J-type is sufficient and preferred. S-type wells introduce a drop after the tangent. This creates an S trajectory, often used for gas reservoirs where zonal isolation during cementing is critical. Approaching the reservoir more vertically allows cement to cover the annulus more uniformly, reducing the risk of gas channeling. However, the trade-off is mechanical. Drop sections create high side forces on the BHA, increasing shocks, vibrations, and wear. Torque and drag are also higher, sometimes limiting the ability to reach TD. The engineer's role is to evaluate reservoir needs versus operational risk. If zonal isolation or regulatory compliance demands it, S-types are justified. But where possible, the simpler J profile reduces risk and cost. The key is aligning design with reservoir objectives while ensuring operational feasibility. When planning a well, thousands of possible trajectories may exist for a given target. The challenge is to refine choices into practical and rational options. Key considerations include avoiding high dogleg severity, accommodating casing and completion requirements, and ensuring hole stability. Geological trends, such as natural build or walk, should be leveraged rather than resisted, as fighting geology leads to costly drilling inefficiencies. Completion method plays a major role. For example, electrical submersible pumps, ESP, require tangent sections, while progressing cavity pumps, PCP, have dogleg limitations. Engineers must also anticipate torque and drag, evaluate hole cleaning capabilities, and ensure that planned profiles do not compromise future production operations. Ultimately, the most effective designs are simple, operationally feasible, and developed collaboratively between drilling engineers and geoscientists. This review summarizes the core learnings of Submodule 2. You should now be able to critically assess how kickoff depth and reservoir entry affect trajectory, feasibility, and well performance. We explored tortuosity and microtortuosity, identifying them as hidden risks that can compromise casing, completions, and long laterals. We examined how shallow versus deep kickoff points influence inclination, measured depth, torque, and drag. Practical examples highlighted how geometric possibilities must be reconciled with lithology, rig capability, and geomechanics. We also contrasted J-type and S-type reservoir entries. J profiles offer simplicity and reduced risk, while S profiles enhance zonal isolation, particularly in gas reservoirs. Engineers must weigh these benefits against the challenges of shocks, vibrations, and higher drag. Finally, general design considerations reminded us that the best well path is not the most complex but the most practical. Plans should be aligned with geological tendencies, completion requirements, and torque and drag management strategies. By mastering these principles, you can design directional wells that are safe, drillable, and optimized for production. This module builds directly on the basics from Submodule 1, completing the foundation of well path design knowledge. Thank you for your engagement in Submodule 2 of Directional Well Path Design. We have now covered tortuosity, kickoff depth, reservoir entry, and advanced design considerations. Together with Submodule 1, this completes the foundation for understanding directional trajectories and prepares you for deeper studies in complex well design. Please progress to the quiz.